Hi everyone, welcome to CS188 Midterm Review Prep. Today we'll be taking a look at some of the concepts that will be covered on Midterm 2. The first question we're going to look at covers probability. So if you read the question, you can see that we have a transition graph structure with three states, A, B, and C. If you look at the graph, you can see that if you're in state A, there's two options you can take. You can either transition from A to A itself with the probability of P, or you can move to B with the probability of 1 minus P. You can also then, when you're at B, either stay in B with the probability of Q, or move to C with the probability of 1 minus Q. And once you're in C, you're just going to stay in C indefinitely. So notice that once you transition to the next state, you can never go backwards. And so knowing all of this, we're going to try to compute some of the probabilities where you might be staying in this graph for multiple time steps and figure out the probability that you're in A, B, or C. So for the first part, we're going to look at the probability that the ghost is at time step, or is at A at time step n. So we know the ghost starts in time step A with a probability of 1 over here. And so given that, we know that for the probability of the ghost to be in time step A, or to be in A at time step n, this is equal to the probability of the ghost transitioning from A to A itself for a total of n time steps. Because at the first time step, the ghost will be in time step or at location A, and then every time step after that, for n time steps, the ghost is going to transition to the state A itself. And so if we think about the probability of that, that's simply equal to P to the n. For our next part, we're going to take a look at the probability that the ghost first reaches B at time step n. So going back to the graph structure we have up here, for the ghost to first reach B at time step n, that means that the ghost must have stayed at time step A for n minus 1 time steps. And then at time step n itself, the ghost will then transition to state B. So we know that in the previous part, in part 1, we've already computed the probability of the ghost staying in time step A for a certain amount of time. And so basically we want to compute then the probability of the ghost staying in time step, or staying in state A for n minus 1 time steps, and then moving to state B. And so the first part of this is simply equal to the probability computed above, but instead of for n steps, it's for n minus 1 steps. And then for the second part, if we look at the graph, to go from A to B, we have a probability of 1 minus B. For the third part, now we're asked the probability that the ghost is in B at time n. So if we think about the graph structure again, for the ghost to be at location B at time n, the ghost must have transitioned once from A to B and not have transitioned from B to C. However, there's some amount of variability that could happen. Like, for example, the ghost could transition from A to B immediately at time step 1 and then stay in B for the rest of the time steps, or it could transition from A to B at time step n minus 1 and then stay in B for the next time step. So we have like some variable with I, and we're going to let I in this case be the time step at which the ghost transition from state A to B. So let I equal the time step the ghost moved from A to B. So now that we have I, we're going to sum over all possibilities of I from 1 to n. And then we're going to compute the probability then for each of these valid sequences that are generated with each of the i's. So this is going to mean the probability for the ghost to move to B at time step I first reaches B at time step I. And we know that we already computed this from the previous part. And we're going to multiply this by the probability that the ghost will then stay in state B for the rest of the time steps. And given that I time steps already passed, then we have n minus I more time steps for the ghost state B. And if we try to compute this probability, we can get a summation from I equal to 1 to n of probability of P of I minus 1 minus P times the probability the ghost stays in B for n minus 1 time steps, or n minus I time steps, and this is equal to transitioning to B n minus I times, each with the probability of Q. So this is equal to Q to the n minus I. And we could try to simplify this down. So on exam, you wouldn't have to. However, you could actually get down to a final probability of 1 minus P, Q to the n minus P to the n over Q minus P. So again, if you work out some of the math, you could eliminate summation, but again, you won't have to if you're asked to just print some numbers on the exam. So now when you consider probability that the ghost first reaches C at time n. So looking back up at the graph, for the ghost to first reach C at time n, this basically means that the ghost would have to first reach B, or would have to be in state B at time step n minus 1, and then move at time step n from B to C. So note that this is very similar to the part we've already done before about the ghost first reaching B at time step n. And like that part, we could basically take the probability we computed in the previous time steps, where we want the probability that the ghost is in state B at n minus 1, and then the probability that then at time step n, the ghost will transition from B to C. And so this is just equal to the previous part, 1 minus P, Q to the n minus P to the n over Q minus P, times probability of B minus C. And if we look back up at the graph, this is equal to 1 minus Q. Okay. So for the last part, we're going to consider the probability that the ghost is in state C at time step n. So like part 3, what we can basically do is consider the probability that the ghost first gets to state C at time step I for some random variable I, and then will stay in time step C until time step n is reached. And this will just consider all the possible cases in which this probably could happen. And so if we do that, we could basically recruit knowledge from the previous part to get the probability that the ghost first reaches C first at time step I. And then we know that ghost is always going to stay in I forever, so the probability that the ghost stays in I is going to be 1. So, and then we want some overall values of I from 2 to n. And so again, we could basically just eliminate this probability because it's equal to 1. Because once you're in state C, you're basically stuck in state C. And so we could basically plug in this probability from the previous part to get summation from I equal to 2 to n of just the numbers we calculated from the previous part. And this is pretty ugly because now we have a summation over a lot of terms. And so you might think of a way to do this with some kind of simpler arithmetic and number crunching. So another thing you could try is to think of this probability in a different way. So for all these probability questions, there's usually a lot of different ways you could compute the final probability. And so for this question, if we're considering the probability that the ghost is time step C at type n, we can instead consider this as the probability of the ghost being in C at n is equal to 1 minus the probability that the ghost is not in B at n, and the probability that the ghost is not in A at n. So notice that we've already computed the probabilities that we need here from the previous part. So this will be equal to 1 minus the probability that the ghost is not in B at n, which is equal to 1 minus P, Q to the n, P to the n, or P minus P, and then minus P to the n. Okay, for question 2, we're going to take a look at completing some queries from a BaseNet. So for this question, some general tips would be that in order to compute a factor, initial factor for a variable for a BaseNet, you're going to basically take your variable, in this case, let's say you want to compute the factor for s. We're going to take probability of s given s's parents. So in this case, the parents are e and m. And so you can see that that's why the factor table we have here corresponds to the factor we computed. And another tip we have is if you join over all the factors for each of the variables, you're going to end up with a joint factor. In this case, it will be the probability of e, s, m, and b. And from this joint factor, you can compute any other factor you would like. So now I'm going into some details of the question. If we read the question, we basically have some variables. In this case, we have s, e, m, and b. And for the BaseNet, we have other tables we would need below. And for the first part, we want to compute the probability that we observe plus e minus s minus m and minus b. And so notice that this is a joint factor over all the variables. So one way you could do this is basically to compute this joint, you could just take the probability of e, probability of m, probability of s given e and m, and the probability of b given m. And if you multiply all these together, you get the probability of e, s, and b. And so because we only want one row of the joint table, we basically just need to take one row for each of the original tables and multiply them all together. And so in this case, we want the row that says minus e. So this is going to be the probability of minus e times the probability of minus m. And the probability of minus s given minus e and minus m. Times the probability of minus b given minus m. And so if you compute all the numbers, we get the probability equal to 0.6 times 0.9 times 0.9 times 0.9 equal to 0.437. Now for the next part, we're going to want to compute, instead of joint probability over all the variables, we're going to compute just the probability of observing plus b itself. So if you observe the factors we have up here, in order to compute plus b, we could basically compute, in this case from these two tables here, we could compute probability of m times probability of b given m. And so we know this is going to be equal to probability of m and b. And in this case, all we have to do is just eliminate the factor for m. So we will want to take sum out over all values of m for the probability m, comma. And so because, again, we only want to compute plus b in this case instead of the entire table, we're just going to take one row from each of these two tables and then eliminate over the possibilities of the m. So this probability plus b is going to be equal to probability plus b given minus m times plus the probability of plus b given plus m by the law of linear probability. And now we can basically compute this as the probability of minus m times probability of plus b given minus m plus the probability of plus m times the probability of plus b given plus m. And so the final probability we're going to compute is going to be equal to 1.0 times 0.1 plus 0.1 times 0.9 equal to 0.1. So for part C, we're going to compute the probability that the mining calculus is occurring given the oils in the boiling. So this is going to be the probability of plus m given plus b. And to compute this is going to be pretty similar to the previous part. In this case, instead of using the law of linear probability, we can use Bayes' rule instead. So we can note that the probability of plus n given plus b is equal to the probability of plus m comma plus b over probability of plus b. And this is equal to the probability of plus b given plus m times the probability of plus m over probability of So for this probability we have over here, we notice that the denominator is already computed from part B, and for the numerator, these are just tables from the factors we have up there. So we could basically just look at the tables in order to get the probability for this being equal to 1.0 times 0.1 over 0.19 value we computed in the previous part. And this eventually gives us the result, 0.526. And now for the fourth part, we're going to compute the probability of plus m given plus s, plus b, and plus e. And so notice that this is again a pretty joint probability with all the variables involved. And we can compute then this using knowledge of Bayes' rule to be equal to probability of plus m plus s plus b plus e given the same probability plus m plus s plus b plus e. However, summed out over and so in this case this plus would be there. And so the numerator again is just going to be one row of the table, and for the denominator this is going to be two rows of the table of the joint factor that we computed. So this is going to be equal to we can sum out over of the variables, or we could join the tables of all the variables again. Yeah, probably plus e plus m, probability of plus s given plus e plus m, probability of plus b given plus m. And so this is the same thing we do for the first part. And for the bottom, we can expand the joint factor in a similar way by computing this as the probability of plus e, probability of m, probability of plus s given plus b and m, probability of plus b given m. And now we can finally just compute the probabilities for all of these variables. And we get 0.4 times 0.1 times 1.0 times 1.0 over 0.4 times 0.1 times 1.0 times 1.0 plus 0.4 times 0.9 times 0.8 times 0.1. And this eventually comes out to be equal to 0.581. And so notice that one tip you can do to save yourself some computation is you can actually cross out everything on the top and bottom, which is not involving the variable m, because it's going to be the same on the top and the bottom. And so this is true because you can see that 0.4 appears no places equal. Okay, so for the final part, we're going to compute the probability of plus e given plus m. And so for this part, we notice that we have individual tables for plus e and for plus m. And so we could basically join these and divide by m. And this might seem weird to you. We could think about why later. So this is equal to the probability of seeing plus e times the probability of seeing plus m divided by the probability of plus m by Bayes' rule. And so you basically have plus m on the numerator and denominator. And this is plus e given plus m is just equal to plus e. And so if you think about this basically just means that e is independent to m. And if we look at our table up here, you can see that indeed, given the constraints of this space net, we do have e being independent to m. So that's why the tables e and m are separate, and we could join them together to get probability of e times probability of m is equal to the factor over both e. And so just in the probability of plus e, we can just read off the table here, and it's equal to 0.14 or 0.4. For question 3, we're going to take a look at Bayes net sampling. And so for this question, we're going to look at the environment where we have 4 actions we could take. We can choose to go north, south, east, or west. And with some probability, we're actually going to take that action and go that direction. However, if we don't go that direction, with equal probability, we're going to choose one of the other directions to go in. So notice that we have basically 4 states we can land in, S, T, and 2 W states. So our goal really is to reach this legendary treasure here. And if we reach that position where we go east, the utility for that is 100. There's also a small treasure with a utility of 25, and 2 whirlpool states with a utility of -50. So we're going to take a look at basically what action we want to take, given we can only make one move, and then we'll land in one of these states no matter what we do. And so, again, we mentioned that you're not going to be able to move directly east if you actually choose to make that movement. There's a certain probability you're going to take that action, and then there's a probability that you're not going to take that action. So in order to compute that, we have this base net structure that tells us basically this probability, which is given by M. And we have a bunch of tables that goes along with it. And we're going to sample from this base net in order to actually compute this probability that we want. So for part A, we're going to use rejection sampling in order to estimate this probability that M is equal to plus M, given -Rn plus F. So the probability that you choose a movement and you actually take that movement is equal to the probability which is given by this M probability. So plus M means that if you go east, then if you actually do the action, there's this probability of chance that you actually do go east. So we've generated some samples from this basenet, and the first task we have to do is use rejection sampling in order to remove some of these samples. So if we take a look at the evidence we have, we basically know that we want -Rn plus F. So if we look at our samples, that means they basically just want to eliminate any samples we see that have either plus R or minus F. So notice the first 2 are immediately eliminated, and this one is also eliminated. So we've eliminated all with minus F, and now we want to eliminate all with plus R. So that's just this additional one here. Okay, and so for all the other samples we haven't eliminated, notice that they all have minus R or plus F as the evidence variables. And so given this, these remaining samples, we're going to want to compute the probability for M to be equal to plus M, given minus R and plus F. And so notice that there are 7 remaining samples we have. And so out of these 7 samples, to find plus M, there really is only one sample here that has plus M. All the other samples have minus M. So basically, the chance in this case that we're going to approximate is going to be 1/7 for this probability of M being equal to plus M, given the evidence that we observe using the sampling technique. And so now we're asked what the ultimate actions for Jasmine and Katie to take are based on their estimate of this probability, and we know the estimate is equal to 1/7. So given that what we were saying earlier, for example, the probability in this case that you want to go east, and so if you take an action is equal to east, and the probability that you actually go east is equal to only 1/7. And so if you don't go east, there's a 6/7 chance that you go somewhere else. So for each of the other states, there's a 2/7 chance that you end up in each of those states. So you could end up in south, north, or west with a 2/7 chance. And so know for this question that the chance that you actually take a direction and you actually go there is less if you directly want to go to that location by taking the action corresponding to that direction. So for example, if you want to head to the treasure, you only have a 1/7 chance of heading to the treasure. However, if you choose not to head to the legendary treasure, you actually have double the chance to do that. And so because of this, we're going to observe that the optimal actions for us to do is to either go south or west, because in each of these 2 cases, if we choose south or west, we're going to have less of a chance of actually landing there. And south and west correspond to whirlpool states, which we do not want to go to. And so for the final part, we want to compute the expected utility for these optimal actions. And so in order to do this, we're going to consider that because this is a random process, we have 4 possible states we could end up in. After taking an optimal action, we can end up in south, west, north, or east. And so for each of these, we're going to want to compute the probability of heading in that direction and landing in that state times the utility for actually being in that state. So for example, we would have the probability of going east times the utility for being in state east plus the probability for west times the utility for west plus the probability that you actually land in state south and the utility for being in that state and the probability that you actually land in state north times the utility for being north. So if you wanted to take a look at the question up here, so north actually corresponds to landing, or going north actually corresponds to being in state S, T, W, or W. So we can use that in order to compute. Like this east actually means that you land in a state with a treasure, and this is state T. West means you're in state W. South means you're in state W. North means you're in state S. And so now we actually want to compute the final values for this. So we observe that, for example, we could pick one of the optimal actions. In this case, let's pick south. And so when that's the case, then the probability of going east is 2/7 times the utility of that is 100 plus the probability of going west is 2/7. And the utility of that is -50 plus the probability of going south is 1/7 times the utility is -50 plus the probability of going north is 2/7 and the utility of that is 25. And so our final utility after summing all of these weighted numbers together is 100/7. So now for the second part, we're going to take a look at, instead of using rejection sampling, we're going to use likelihood weighting in order to compute the samples and then compute the final probability that we want for this value. And so to do this, we're going to look at a bunch of samples and assign weights for each of them. Recall that for likelihood weighting, the weight for a sample is going to be equal to the weight or from the tables for each of the evidence values that we observe. So in this case, if we look back at the tables, we're interested in the variables R and F. And we basically want the tables corresponding to R and a table corresponding to F. So in this case, the probability of, or the weight then we would assign to the first sample is going to be equal to seeing -Rn plus F, given everything we know, which is going to be equal to the probability of -R times the probability of plus F given plus W. And so for the particle below, we have the particle, or the probability -R times the probability of plus F given minus W. And then for here, we have the probability of -R times the probability of plus F given plus W again. And for the last one, this is going to be equal to the same as the second one, so minus W. So for this first weight, this is going to be equal to 0.6 times 0.15. And for the second one, this is equal to 0.6 times 0.75. And so this is equal to 0.09, and this is equal to 0.45. And we can do the same thing for the next two parts to get 0.09 and 0.45. And so given these four samples, now we can compute the actual approximation we make for this probability that we're interested in. And so notice that we have plus m in two of the cases here and minus m in the other ones. So the total sum of the weights we're going to have is equal to 0.09 plus 0.45 plus 0.09 plus 0. The total sum that we're going to divide by is equal to the sum of the weights of all the samples, and the weights we're going to put on the numerator is equal to the weights of those where m is equal to plus n. And so that's going to be equal to 0.09 plus 0.45. And notice that this is equal to precisely 1/2. And so given this probability is 1/2, that basically means if you choose an action to go east, you're actually going to go east with 1/2 chance. And so with a 1/6 chance, you're going to land in any of the other non-east directions. And so knowing this, this is different from the previous part where
if you actually choose to go east, you have less of a chance to actually land in that state. Here, because you have a more of a chance to land in that state where 1/2 is greater than 1/6, you actually do want to choose east to move in, given this probability estimate. And so our expected utility, we can compute with the same as the previous part, where we have 0.5 probability of going east times the 100 utility we get for doing that, and then plus 1/6 chance for landing in each of the other states, times 25, plus 1/6 times -50, plus 1/6 times -50. And so our final probability is going to be equal to 75 divided by 2. So for the third part, we're going to take a look at using Gibbs sampling now in order to compute the estimate for the probability value. And so for Gibbs sampling, we start off with our evidence the same as before, which is minus r n plus f. And we also have a random sample that we begin with, which is given plus e minus w n plus m. And so from this sample, we're going to choose, again, so we're calling Gibbs sampling, we're going to choose a random variable, in this case, variable e, in order to resample. And so if we resample that, then we actually want to compute the value for this, which is going to be equal to probability of plus e given minus r minus w plus m and plus f. And so this is going to be the probability that you sample plus e, given that we want to resample variable e. So for this, recall that this looks like a joint probability, which is very similar to what we have in question 2. So we basically can compute this as, for example, the probability of E, R, W, M, and F, given this the same probability, E, R, W, M, and F. However, after eliminating this variable E. And by Bayes' rule, this is going to be the same as the query we want. So to compute this probability from the factors we have, we can expand out the join as a product of factors. So on a numerator, we would have probability of R, probability of E given R, probability of M given E and W, and probability W given R, probability of F given W, all multiplied together. And on the denominator, we would have the same thing except summed over the variable E. So this would be probability of R, probability of E given R, probability of M given E and W, probability of W given R, and the probability of F given W, all joined together. And so if you notice, there's some shared variables on our numerator and denominator, which actually do not involve E. So we can actually eliminate them first in order to save us some compute, because they'll be the same regardless of summing out E. And so that leaves us with a smaller summation and end product that we can actually compute more easily. And so if we do this, we can basically just multiply together values for each of these. So we could have the probability of plus E given minus R, probability of plus M given plus E minus W. And so this is just from assigning values to all these variables, which we have from the factor generated. And on the numerator, on the denominator, we're going to have the summation, which is going to be applying the law of total probability, basically, over a variable E, plus M given plus E minus W, plus the probability of minus E given minus R. So in this case, here we're going to use either plus E or minus E. And so this probably all boils down to being equal to 0.6 times 0.45 from looking at the probability tables we have above, times the probability of 0.6 times 0.45 plus 0.4 times 0.9. And finally, this gives us the weight 3/7. And so now we notice that we're going to now resample for a long time until we finally end up with one sample remaining, the same sample, which is minus R minus E plus W plus m and plus f. And so Jasmine and Katie are happy with fixing this one sample. So they will only use this one sample, approximate the distribution. And so given that we just use this one sample, the approximation we're going to have is going to be equal to 1, because it's basically equal to 1 over 1, because from the one sample we observed that this one sample has m is equal to plus m from it. So from our knowledge, like, it's going to be guaranteed from this one sample that we end up in a state plus m. And so given that this is guaranteed, that m is equal to plus m, the optimal actions Jasmine and Katie should take is going to be east for sure, because this basically means that if I want to head east, I'm going to end up in the state east with 100%. There's no other chance that I could end up in south, west, or north. So we're going to head directly to the legendary treasure, and we're going to actually get the treasure from all we know, given this probability estimate of 100%. And the expected utility then will be 100 times 100%, because there's a 100% chance that we end up in the state with the treasure, plus a 0% chance of everything else. So we can basically just ignore that.
Okay, so in this problem, we're going to be discussing probability and decision networks. So the setup of the problem is that there's this movie Skyrise, and it's either going to be really good or really bad. So it's going to be plus m or minus m. And then the way we're going to act in this problem is that we can either go see this movie in the theater or we can rent it at home. Okay, and then on the right of the BaseNet that represents this problem, there's the probability tables, and there's also like the table that tells you the utilities of each possible scenario. Okay, so you can see that it's equally likely to be good or bad, and then there's these different utilities for seeing it in theaters versus renting it, depending on how good the movie is. Okay, so for part A, it asks us to compute several quantities. The first one is expected utility of seeing it in the theater. So the way we do it, of course, is just weighting each possible scenario by the probability that it happens. Okay, so this would be the probability of that the movie is good times the utility of the movie being good and seeing it in theaters, plus probably the movie is bad times the utility that the movie is bad and we see it in theaters. So that's okay, so that's this quantity. And then we can just read off the relevant terms we need from the table and then just calculate this. So the probability that it's good is 0.5. The utility of it being good and seeing it in theaters is 100. And then let's see, probably that it's bad is also 0.5. Ooh. And then the utility of that is 10. Oh man. Okay, so overall this comes out to 55. Okay, and then they want us to calculate like the other quantity, which is the expected utility of it being rented. So again, we're going to calculate like this weighting by the probabilities. Plus the probability that it's bad times the utility in that scenario. Oh, excuse me, this is rent. Okay, so then this will come out to 0.5 times 80 plus 0.5 times 40, and this is 60. Okay, so then they want us to find the maximal expected utility, and the way we do that is essentially just choosing the action that has the higher expected utility. So this is max of 55 and 60. So 55 corresponds to seeing it in theaters, and this corresponds to seeing it like when you rent it. So the maximal expected utility is the quantity. It's like the expected utility of the best action. So this will be 60. And then the action that achieves that is renting it. Okay. Okay, in part B, they've introduced these other variables that kind of let us figure out whether a movie is good or bad. So now there's, in order to figure out that the movie is good or bad, we can see if people in the UK eat fish and chips, which is also affected by whether or not there's a food shortage, which is S in the diagram. Okay, and then of course there's the probability tables of each of the scenarios, and we're interested in finding the value of the food shortage node S. So we're trying to find these different quantities. Okay, so our first observation is that the utility of choosing a certain action only depends on the action we take and also the quality of the movie. But if you look at the diagram above, S is actually independent of M. So what that means is that if we learn S, we don't actually know anything more about M. So the expected utility of going to see it in the theater conditioned on the fact that there is a food shortage means that there's no value in knowing this. So the expected utility is actually the same. So it's just the exact same quantity as from part A. So this is 55. This will be 60. The maximal expected utility, when you know that there's a food shortage, that's still the same as if you didn't know anything or if there's no food shortage at all. So that's still the answer from part A, so that's 60. The optimal action is still the same, which is renting. And yeah, and then if there's no food shortage, that still doesn't affect our decision, so that's 60. The optimal action is still rent. Okay. So then the value of perfect information of S is trying to tell us how much better is it on average to know S than to not know S. And since the information that S tells us isn't actually relevant at all to what we care about, which is the quality of the movie, the value of perfect information is 0 for this. Okay. And this all comes from the fact that the food shortage variable is independent of the quality of the movie. So none of its values will tell us anything interesting about the quality of the movie. Okay, question 5 is a hidden Markov model question which discusses the interaction between this human and a robot. So every time step there's a human action which directly causes some sort of observed evidence for that time step. And the robot will see that observed evidence and then it will have its own action. And together, the human action and the robot action will influence what the next human action of the next time step will be. Okay. So in this problem, we'll be observing the evidence and the robot action, and then using those to update our beliefs about the human action at every time step. Okay. So this problem will have 2 parts. There's a time elapsed update expression, and there's an observe update expression. Okay. And then in part A, we'll be trying to find this observe update expression, which is this. O of h of t is equal to the distribution over the human action conditioned on all the evidence and all the robot actions up to that time step. Okay. And then one thing that will kind of guide how we do this problem is the fact that we're given like this quantity, the probability or the distribution over the current human action conditioned on all the past evidence and all the past robot actions. Okay. So yeah, so let's get started. The distribution over the current human action conditioned on the current evidence and the current robot actions. We'll be splitting that into the current action and the current observation and like all the past evidence and past robot actions. Okay, so, and that's just because it will match exactly what we did over here with what we're given in terms of the distribution over the human action. So this is h of t conditioned on the current evidence, the current robot action, and there's all the previous evidence and robot actions. Okay, and then the way we approach this is kind of through a Bayes rule type of thing, where we're given a lot of these conditional probabilities, and we use them to calculate this quantity, which is what we're interested in. So this is the probability of the current evidence and the current robot action conditioned on a certain human action as well as all the past evidence. This is times the probability of the human action conditioned on all the past evidence. This is the quantity that we're using from above. Okay, and then this is all divided by the probability of these two current observations conditioned on like the past observations. Okay. So then how are we going to find these terms? Essentially this is so first what we can note is that conditioned on HT, ET and RT are independent on the past evidence and the past actions. So we can just simply write this out as the probability of that current evidence conditioned on HT times the probability of that certain robot action conditioned on ET times probability of HT given all the past evidence. Okay, and then this will be divided over basically the sum over all the different possible human actions at HT. And this is the probability, like this is essentially the term on the top, because this term on the top is the probability of HT, ET, and RT. And then when we marginalize over HT, we're given the quantity that we want over here. So this is P of ET given some particular human action times P of the robot action conditioned on that times the probability of this particular human action conditioned on all the past evidence. Okay, and then at this point we're basically done. All we have to observe is that these two terms are the same, and then we can go back and look at the choices. So if you look at all the choices, there's only two of them that match the form that we have. It's the first one and the second one, and the only difference between the first and the second one is that one will cancel out these two terms that are the same, and the other one doesn't cancel them out. Okay. Next, we're going to do the time-lapse update, which is essentially where we have the distribution over h of t minus 1, and then we go to h of t without observing like new evidence and the new robot action. Okay, so again, we're trying to calculate this quantity, the distribution over the current human action given all the past evidence. And essentially, this is what we can calculate is that this is a marginalization over all the past human actions. So this is h t minus 1, probably h t minus 1 conditioned on all the past evidence. Okay, and then we can just simply use our conditional independence assumptions, and then what happens is that we get first we can use the term that they give to us, and this is probably of like that past action conditioned on all the past information that we know. And this is times the probability of the current action given the previous human action and the previous robot action. Okay, and then the reason why there's no evidence variables in this is because those are conditionally independent given these two. Okay, so then the answer for this is just the last term that we got, which is the sum, like we marginalize out the past human action, and we multiply the probability of that past human action conditioned on like the past beliefs times like essentially like the transition probability from the past human action to the current human action when you also know the robot action. Okay. So for question 6, we discussed naive Bayes and the different assumptions it makes as a classifier. So what kind of assumptions does it actually make? There's only actually really one that's really important, and it's that it assumes that features are conditionally independent when you're given the class. So once we, so like if you're given the class, the value of one feature or one dimension shouldn't affect the probability distribution over another feature. Okay, so knowing that, let's go through and look at these different problems and see which ones satisfy and which ones don't satisfy the modeling assumptions. Okay, so for part A, we see that one class is kind of like this square shaped, while the other class is arranged in this rectangle that goes diagonally from the top left to the bottom right. So looking at this class, the big problem here is that the two features are actually not conditionally independent when you're given the class. So for example, if you're given that the feature of f2 is 3, then the domain of the feature 1 is just these 2 points. But if you're given the feature, or if you're given that f2 is 1, then there's like a vastly different domain for feature 1. So what that says essentially is that these two features aren't conditionally independent. Like one value will affect the other, so it doesn't actually satisfy the modeling assumptions. Now that isn't to say that naive Bayes won't be useful. All it says is that we violate the modeling assumptions and there will be like some sort of imperfections in when we translate from this model to the real world. Okay, so let's move on to part B. And for part B, we see that both classes actually satisfy the modeling assumptions. So no matter what value of f of class 2 or class 1, we see that the two features are conditionally independent. Like knowing one value won't change what you think about the other one when you're actually given the class. So this one satisfies the assumptions. Okay. For part C, we see that the two classes do overlap, but this doesn't affect whether or not the modeling assumptions are violated. Like the two features are pretty clearly independent of each other when you're given the class, but the only interesting thing to note here is that naive Bayes won't be able to perfectly classify these two because of the overlap. But regardless of whether or not it can perfectly classify the two, the way that these two classes are set up, they will satisfy the naive Bayes modeling assumptions. Okay. And then D, again, because these are like perfect rectangles that are aligned along the axes, knowing one feature doesn't affect what you know about the other feature, so this satisfies the naive Bayes modeling assumptions. And then for both E and F, again, you see that they're slanted, so knowing one feature affects what we think about the other, so they're not conditionally independent given the class, so neither of these will satisfy the modeling assumptions of naive Bayes.